47 years ago, a golden spacecraft no larger than a small car slipped quietly into the void, carrying the dreams of an entire planet. What began in 1977 as a bold mission to explore Jupiter and Saturn has become something far more profound. Voyager 1 is now humanity's most distant emissary, drifting more than 15 billion miles from Earth into the vast unknown of interstellar space. In 2012, it crossed the heliopause, the invisible boundary where the Sun's influence ends and the galaxy begins, becoming the first human-made object to do so. Now that the NASA Voyager 1 has reached the other side, we know that it's totally not what we thought. Today, we'll zoom out and see where we are in the cosmos. Mapping the interstellar medium. Since crossing into interstellar space in August 2012, Voyager 1 has become the first and only spacecraft to directly study the interstellar medium from within. With three primary instruments still operational, the magnetometer, the plasma wave subsystem, and the cosmic ray detector, Voyager 1 has transformed our understanding of what lies beyond the heliopause. Contrary to long-standing assumptions that interstellar space is an empty void, Voyager's data has confirmed that it is a dynamic, highly structured environment marked by turbulence, shifting plasma densities, and magnetic irregularities. The spacecraft's magnetometer, a fluxgate sensor developed by NASA's Goddard Space Flight Center, has been crucial in mapping the local magnetic field outside the Sun's influence. After crossing the heliopause at approximately 121.6 astronomical units from Earth, or about 11.3 billion miles, Voyager 1 began detecting unexpected changes in magnetic field direction and strength. These magnetic anomalies suggested that the Sun's magnetic field was still interacting with galactic forces beyond the heliosphere in ways scientists had not anticipated. The magnetometer recorded fluctuations and sudden shifts. These fluctuations redefined our understanding of the cosmos altogether. Complementing this data, Voyager's plasma wave system has provided an acoustic-like map of interstellar space. The plasma wave subsystem, built at the University of Iowa under Don Gurnett, monitors the frequency of plasma oscillations, allowing researchers to measure the electron density of the surrounding medium. One of the most significant discoveries came in 2013 when, months after crossing the heliopause, Voyager detected an oscillation triggered by a solar outburst that had traveled outward and disturbed the interstellar plasma. The oscillation's frequency allowed researchers to calculate the plasma density, which was substantially higher than the near vacuum inside the heliosphere. This single event was key in confirming Voyager's entry into interstellar space. Another major contribution came from the cosmic ray subsystem, which has been operational since launch and is now helping researchers chart the density and composition of high-energy particles outside the heliosphere. This instrument, developed at the University of Chicago, has detected a marked increase in galactic cosmic rays since crossing the boundary. Inside the heliosphere, the solar wind shields Earth and other planets from many of these cosmic rays. Voyager's detection of a 9% rise in cosmic ray intensity served as further confirmation that it had left the solar bubble and entered the more exposed galactic environment. Perhaps most striking is Voyager's revelation that the interstellar medium contains weather-like phenomena on a scale incomprehensible to Earthbound observers. Scientists have identified interstellar cloudlets, which are localized, high-density regions of plasma that Voyager passed through in 2020 and again in 2022. These cloudlets, likely just a few hundred astronomical units wide, caused sudden shifts in plasma density by factors of 2 to 3. Additionally, the spacecraft has recorded large-scale filaments, or extended structures resembling cosmic rivers of charged particles, as well as signs of shock fronts caused by supernova remnants. These findings suggest the interstellar medium is not static but in constant flux, shaped by ancient stellar explosions, magnetic turbulence, and gravitational forces. One of Voyager 1's most enduring contributions is the realization that the space between stars is anything but featureless. Earth-based observatories and space telescopes like Hubble or the Chandra X-ray Observatory have hinted at the interstellar medium's complexity, but none have been able to sample it directly. Voyager 1, launched nearly 5 decades ago, now functions as a remote sensor embedded in that cosmic terrain. Each signal it sends, traveling over 22 hours to reach Earth at a data rate of just 160 bits per second, carries unprecedented information about a part of the universe never before touched by human technology. But wait, there's more. The local interstellar cloud and the local bubble. Voyager 1 has confirmed that our solar system is currently embedded in a region known as the local interstellar cloud, a relatively dense pocket of gas and dust nestled within a much larger structure called the local bubble. The local interstellar cloud, also known as the local fluff, is approximately 30 light-years wide and has a density of about 0.3 atoms per cubic centimeter, significantly denser than the surrounding regions of the local bubble, which may have densities as low as 0.05 atoms per cubic centimeter. Voyager 1, using its plasma wave subsystem and magnetometer, has detected these density variations directly by measuring electron plasma oscillations and magnetic field fluctuations as it travels deeper into interstellar space. NASA scientists believe the solar system has been moving through the local interstellar cloud for roughly 60,000 years and may exit it within the next 10,000 to 20,000 years. This cloud is not uniform. Its density and magnetic strength vary considerably, contributing to a patchy and irregular structure. The local interstellar cloud itself is just one small feature within the local bubble, an enormous cavity in the interstellar medium that spans roughly 1,000 light-years in diameter. This bubble was carved out by a series of supernovae that occurred around 10 to 15 million years ago, originating from now-extinct massive stars in a region that once belonged to the Scorpius-Centaurus OB stellar association. These supernovae blasted away the dense interstellar gas that previously filled the region, creating a vast, hot, and low-density void filled with thin plasma. The walls of the local bubble, its boundaries, are denser regions of gas and dust, effectively forming a shell that separates it from adjacent cavities in the interstellar medium. This bubble is not empty. It contains several well-known star systems, including Alpha Centauri, Sirius, Procyon, and Altair, all located within the local bubble. The Sun's motion through this environment at approximately 450,000 miles per hour, or 720,000 kilometers per hour, means it is continuously interacting with the ever-changing conditions of this interstellar cavity. One important effect of being in this bubble is how it alters the permeability of cosmic rays. Voyager's cosmic ray detector has observed changes in cosmic ray intensity that correlate with the structure of the bubble and the presence of denser or magnetically shielded regions, such as the local interstellar cloud. The interaction between the solar system and its galactic environment also influences the heliosphere, the protective bubble formed by the solar wind. As the solar system moves through different regions of the local interstellar cloud, changes in external pressure from the surrounding interstellar plasma can alter the shape and size of the heliosphere. A denser or more magnetized region in the local interstellar cloud, for example, may compress the heliosphere, reducing its ability to shield the inner planets from galactic cosmic rays. These interactions may have subtle but real effects on Earth's climate and radiation environment over geological timescales, possibly affecting everything from atmospheric chemistry to biological mutation rates. Thanks to Voyager 1, scientists can now directly measure the properties of these surrounding interstellar structures rather than relying solely on remote sensing or modeling. As the Sun continues its orbit around the Milky Way, completing one revolution every 230 million years, our solar system will pass through many such interstellar regions. Voyager's findings serve as a crucial baseline for understanding how these galactic environments shape the evolution of planetary systems. The heliopause and beyond. Voyager 1's crossing of the heliopause in August 2012 marked humanity's first direct venture into interstellar space, but the data it continues to transmit has revealed that this boundary is far more complex and dynamic than once imagined. The heliopause is not a fixed or smooth shell encasing the solar system, rather, it is a fluid, constantly evolving interface between the solar wind, a stream of charged particles emitted by the Sun, and the interstellar plasma that permeates the space between stars. The Sun and its planets are constantly encountering new regions of interstellar space, each with different densities, plasma pressures, and magnetic field configurations. As a result, the heliopause is not a clearly defined shell, but a shifting boundary shaped by external and internal forces, sometimes stretching outward when solar activity is strong and retracting when the pressure from interstellar plasma increases. Voyager 1 provided groundbreaking measurements that confirmed the heliopause lies at a distance of approximately 121.6 astronomical units from the Sun, though this can fluctuate depending on conditions. One of the most remarkable discoveries made shortly after the crossing was a dramatic spike in plasma density, as measured by the spacecraft's plasma wave instrument. While Voyager's direct plasma sensor had failed years earlier, scientists were able to detect ambient electron density by measuring the frequency of plasma oscillations caused by solar eruptions. The jump in density was a critical confirmation that the spacecraft had truly left the Sun's domain. Equally surprising was the behavior of magnetic fields beyond the heliopause. Based on earlier models, it was expected that the magnetic field direction in interstellar space would differ significantly from the orientation of the heliospheric magnetic field.